All right, welcome everyone to another episode of RoboPapers. Super glad today to have Jiafei, who's a repeat. I think Jiafei was our first guest. Good to have you again, Jiafei, as well as his colleagues, Jason Lee, as well as Haoquan Fang. Three of the authors from this paper called MolmoAct, Action Reasoning Models that can reason in space. Thank you so much for making the time, guys. Really looking forward to this one. I think it's an awesome thing that you guys did here, like open source, basically everything. But maybe as a start, if each of you can give a quick intro about yourself, maybe starting with Jiafei.
Yeah, thanks, Michael. Sorry for the muffled sound, but I think thanks, Michael, thanks, Chris. I think this is like my second time on the show, and ever since the first video came out, I think many people actually came to me and say, they watched the video from like RoboPaper, and then they were like, it's pretty cool. And I think that's all of this to all this, right? So I think just for the audience that doesn't know me, my name is Jiafei. I'm a third year and sort of graduating PhD student this year. I'll be on the market. And I'm working on mostly robotics foundation models, robot learning. And I think these days a lot on towards like grounding vision language models for robotic manipulation. Yeah, I work with Professor Dieter Fox and Ranjay Krishnan.
So hi everyone, my name is Jason Lee, and right now I'm a master's student at University of Washington, and I'm also working with Dieter Fox and Ranjay. I'm working a lot. I mean, for the past year now on MolmoAct, so like all these different robotics foundation models, and I'm also looking into other more on the data side, new ways to generate robotics data. And then I'm a collaborator at Allen Institute for AI. So there's what we.
So can you hear me? Because I'm actually talking to another computer.
Yeah, we can still hear you.
So my name is Haoquan Fang. I'm also a student collaborator at AI2. I'm also a undergrad student, third-year undergrad, rising senior. I'm majoring in computer science at UW. I actually heard of the RoboPaper from Jiafei last time. Was that for SimplerEnv? Yeah, I'm also an author of SimplerEnv. I'm glad to be presented this time for MolmoAct. Thanks for the opportunity.
Awesome. Cool. Great to have all three of you here.
So I think the whole notion is that, we want to show that we're able to deploy MolmoAct in this environment to do not just like a single short horizon task, but a long horizon task, such as, making me a breakfast. And I think the hard part here is how do you first of all ensure that you're able to get the model to really efficiently fine-tune for these downstream tasks in an environment that is. Also, to be honest with everyone here, when we test this and what we collect the data, the environment looks a bit different, and we didn't know about this completely. The filming crew came in, they have all this spotlight, and when you have this lighting, you're going to make things really hard for a lot of these policies. So and this is something that we just run it, and in the first go somehow it actually works pretty well and able to get the task done. And I think also in this video, maybe Jason can play the video. Yeah. So in this video, it started with me talking, and then there wasn't any speed up, but you can see that it's actually moving in this like action chunk motion where it takes 8 steps, and then it infers, it reasons, and it predicts the next 8 steps. So I think and in the subsequent video, as we speed up, we also put down there what's the speed up time, and we also sort of have a sense that it's kind of not the fastest model that's out there, but I think this is also the early days where Pi-0 when they first started, they're also looking at 8 to 6 times speed up. And I think it's even more so because we are action reasoning model, and we are predicting not just the direct action, but there's also a lot of reasoning tokens in front of that in a fully autoregressive manner. Yeah, I think the next part, Jason could share a bit more about what's going on. That's him.
Yeah, so like I think a big part of MolmoAct right here is like we were trying to introduce or incorporate the notion of reasoning, and specifically like reasoning in space, into robotics. So like a lot of these robotics model, they do perception, planning, and action in like just like in a one-step sort of way. So these like VLAs, they take an input image and a language instruction directly, they just output action. But I feel like, I think with MolmoAct right here, we're trying to predict these. We first lift the whole scene into 2.5D with our depth map. So we can kind of create these, we did like these point cloud visualizations in the video. And then we also show what we call these like visual reasoning traces that our models predict before actually predicting the action. And then this is also sort of help us to ground the action into like the observation image. And then I think the big part of MolmoAct here is we think that this is more effective than reasoning in language or in text, because ultimately like these motions, these like physics and robotics, there are they're more naturally, more intuitive in space compared to like trying to describe all these motions in language. And then when you try to, like distill all these motions down into like what the Wikipedia text format might look like, you lose a lot of complexity in the translation. So because basically showing that reasoning works in robotics, and this is our main point here. And then we also show that there's some downstream effects such as steerability that comes from this reasoning. And Haoquan, you can kind of talk us through what is steerability.
Yeah. So thanks, Jason. So maybe you can start first. So we want our model to be a generalist, intelligent robotics policy that can think on its own, like what we call reasoning. And we also want it to be steerable or comfortable. We want user to interact with the model the responsive way. So in our case for MolmoAct, say we can prompt the model by drawing a visual trace on top of it. So this is the line we draw it. So in this scene, we let the model, we just prompt the model to say like, just to pick up the ball. And then this yellow trace here shows what the model thinks. So that's in the reasoning part, because the model will output internally on what's the depth and what's the planning through a visual trace. So we can see that the model initially wants to pick up this is the red ball, I guess. And then after that, the user comes in, and then we overlay a line, this blue line, onto the image, and then let the model think again. And we can see that the model will then goes to the other ball. So the user can just come in and interrupt the intended plan or the new.
So can you explain a little bit more about what you mean there when it's predicting, when you're saying it's drawing that blue line? Do you literally mean it's predicting that image with the blue line? Do you mean it's predicting like a 3D trajectory in space? Does it have the ability to do both? Can you go into a little bit more?
Sorry, can you repeat the question? It's a little soft. Like the sound is a little bit.
I was
quiet.
saying when you were saying like it was drawing this blue line for the trajectory. It's like literally drawing an image, like generating an image on this. Is it a 2D trajectory, a 3D trajectory? What can it handle?
So for now, we only overlay a 2D trajectory onto the image, but we also think that depth is also an important portion, and it should be incorporated into the steerability process. Because we also found some try to steer the robot. It might be a little bit hard for us to tell the robot like where to go in terms of depth. And I think works for just to steering in certain directions. And I think our future work might contain like how do we incorporate depth into the steerability process. And I think it's an open question.
And then I think just to re-emphasize this again, so I was saying earlier throughout the reasoning process, MolmoAct first predicts depth and then line and action. So when it predicts this line, it's this yellow line over here. So like initially the language instruction is pick up ball, but there's two balls, so it's a little ambiguous in this case. So MolmoAct decides to first try to pick up this red ball, but then what Haoquan was saying right here is that this blue line is now human input. So we draw this blue line just pointing out where each points in this line is, and then we overlay this blue line onto the observation image, and then feed it back into MolmoAct as input, and then we show that MolmoAct will follow this blue line instead of the original yellow line. So the yellow line is MolmoAct prediction, blue line is human drawn. Part of this work is also because of what is in our data mixture. So we train on these like trajectory condition data. So it's not only language condition. So during training, we overlaid the line onto the robot image and asked it to predict action. So if that clarifies your question.
Yeah.
Any other question about steerability?
I think also like just to add on here in like a high level, I think a lot of times we say that MolmoAct is open, right? So I think open, it doesn't just mean in the sense of open data, open weights, and open checkpoint, but also in the sense whereby the model being open allows people to be able to diagnose what actually goes down under the hood. So providing this additional layer of interpretability that comes naturally from our model's prediction, I think that actually is really, really interesting, because talking to many people from doing like humanoids, when you try to deploy a humanoid in the household, you have no idea what the humanoid is going to try to do next. You can throw a policy into it, and there's no way for you to have a forecast forwards in time to sort of express the intent that the humanoid might be acting upon. So we realized that actually when MolmoAct is outputting this visual trace, when users are looking at them, they have a sense that, okay, where this is exactly going towards. By knowing exactly where it's going towards, and then it give you more control to, okay, maybe that's not what I intend to, and there is this like ambiguity in language as well. Haoquan just mentioned, you're able to sort of steer it. And maybe we can dive deeper later into the individual experiment. We'll show that why in some of these experiment using open language to sort of steer is not as great as using the visual trace that we have designed here.
Yeah, cool. I can also dive deeper into how we do this reasoning first. So, in our MolmoAct, I start with like kind of the data mix. So this is like a very high level overview. So we train with some robot data, and then we train with also like multi-model web data, and then some auxiliary data to kind of assist our reasoning process. And then this is like the main reasoning in space, which is, given this language instruction, I put the plate in the dishwasher. We first predict these depth tokens. I'll also go into details on how we generate these depth tokens later. And then after it predicts these depth tokens, it started predicting these visual reasoning trace. These are also in text tokens, but these are essentially like 2D waypoints of this line. And then after it predicts both of these, then it predicts the action. So it's just doing this condition in a very explicit, like autoregressive format. So we can dive deeper here. So you can see that at first, during like training, we have this pre-training first, where we just predict all these sort of different modes of data. So you can see like the trajectory condition data that we were talking about here. So partly like we overlay this line on the image and ask it to predict action directly based on the trajectory. And in this same data, we also have just like the image without the overlay, where it kind of gives a task and then it predicts the depth, the line, and then the action. So it's like the same image, but it's going through like different form of conditioning. And right here is like our post-training case, where we also like train MolmoAct based on our MolmoAct dataset to take in multi-view images. So it's just in the pre-training phase, we only take in the front view image, but in like later on in this like our mid-training and post-training stage, we take in like these wrist view image as well. And then similarly, it does like this depth token prediction, visual trace prediction, and finally the action tokens. And then we can show that also be adaptable to like bimanual setups. And then we try like with like humanoid setup with like with the unitary stalks with the arm mounted on top. So like it's like adaptable to also different embodiments. And then you can see like even like the visual reasoning trace is not limited to just a single arm Franca. We can also deal with like bimanual by predicting the trace of both hands. So, different things like that. And then this is also be able to take in input of whether it's just you want to just to condition on the language, or also give it your own like trajectory layer on top of it. Yeah. And then, to really enable all of this process, this is like our main crux of MolmoAct is our data mixture. So we can go into like our action reasoning data, which is just basically the formulation of this depth and then visual reasoning trace and then the action prediction. But then we also train with a bunch of these auxiliary data. So like auxiliary depth perception data is just given the image, we ask it to predict the depth token without the action. And then auxiliary visual trace, same idea, is really just to given the image, it will just predict the trajectory without action as well. And then the auxiliary trajectory condition data is just basically taking the image with the trajectory overlay on top of it and predicting the action. So these are without reasoning. And then kind of to like wrap all of these up together, we have the action reasoning data, which is just given the observation image, it will predict depth, predict line, and then predict action in the autoregressive formal way. And then, Haoquan, if you kind of want to talk about how we generate these depth tokens.
Sure. So to enable the model to...
Sorry, Haoquan. Yeah.
No
One
worries.
quick question. So I think this is a very interesting data mix. Like, can I ask a few questions about this? So I know that some of these come from, for example, you have this multi-model web data. Like, where do they come from? I know you guys take a curated version from OpenX.
Mm-hmm.
So could you talk about the whole process like a bit more? Where do the data come from? And how do you guys end up with this mix?
Okay, so this is just pre-training. The multi-model web data, a lot of it is coming from Momo, which is our base VLM. And then essentially the intuition is you want to retain the capabilities of Momo. So, Momo is like really good at pointing, and then these like spatial reasoning, object localization sort of things. So that's where this multimodal web data is mainly curated from. So it's a lot of this like from Momo's Pixmo. So Momo has like these dense detailed captions. So we train a lot with that. And then we did like list out where all of these like details in the paper. So for example, we list out all the mixture here. So Momo's academic data sets. We train with like these Pixmo, and we train with the Elvis, which is like the bounding box data. So this is like the multi-model web data that we're training with. And just keep in mind, this is all just in pre-training as well. And then furthermore, in like the auxiliary depth perception data and visual trace data. So these actually, I would say like rest of all of this are from all OpenX embodiments. And then we're just using Fractal, and then which is like the RG1 data mix data set, Bridge version V2, and BCZ. So, these, even like just one data set, for example, like you take Fractal, Bridge, and BCZ, is not a very big collection, but you can generate different types of data with it, like trajectory condition. You can generate the depth perception data, so visual reasoning trace data. So a lot of these data have different overlaps, even though we're training for like different. So like the same sample could be used for as an auxiliary task as well as like the action reasoning data prediction. So ultimately, I think we list our sample rate also in here.
I think also to add on to a point that Jason is mentioning, right? So I think ultimately when we first did this, it's a learning lesson for us to sort of learn how to build, the action reasoning model. And one of the interesting takeaway that we realized is that you shouldn't use the full OXT embodiment data for your pre-training. And I think this is not just something that came from us. I think like Alan from Princeton, when he did the OpenPy implementation, he also only uses a fraction of OpenX embodiment. And we realized that actually that yields better performance than what OpenVLA uses, which is the full component of OXT embodiment. And a lot of times, because in OXT embodiment data set, there's mixtures of data that has really poor resolution. It has data that language that's not aligned to exactly what the task is doing. There's also data whereby you're just doing random stuff, like data that has a huge duration of no ops period, and that's really bad for training. So these are some of the things that we look into and try to filter out when we use OpenX embodiment. Yeah. So for anyone who also want to download the filter version, it's also on our dataset cards on Hugging Face. Yeah. So we actually filter one round.
Yeah, it's all on this Hugging Face pre-training mixture right here. So, and then we also have like mid-training, which is just essentially we curated our MolmoAct Dataset. So this is based on like real-world household environments. So we have basically two. So we have home environment data, we have tabletop data. So essentially home environment data is in like kitchen, bedroom, living room, things like this that we curated at home based on the Droid setup. And then, we try to just make these like very high quality trajectory, and then also capture like different views. So we have a primary view and we have essentially two side views and a wrist view for this data set. And then we try to, also decompose like some long horizon household tasks down into like more like, let's say, for example, clean up dishes can be decomposed down into, or put the fork in sink, cover the pot, etc. And then we also reinforce all of these, there's like a lot of atomic motions. So for example, like based on this task, like put the pot in the dishwasher, there's like open, pick, flip, put, close that you have to do throughout to complete this task. And we, reinforce it in a tabletop environment setting. And then again, this is all available on Hugging Face. So we have two views that we manually, label themselves. So primary view is like what we consider like a clearer view of the view that we think is better. And then we have a secondary view. And then, so we have for the home environment and for the tabletop environment. And then this is what we use for mid-training. You can kind of explain the training procedure for MolmoAct.
Yeah, that sounds like a lot of work, man. Whatever you just described, it's all done in-house, like the labeling, putting it into atomic actions, like, what is put, what is open, different scenes.
Great question, Michael. As I said, like this is our sort of like our first attempt and looking, and so we are fortunate because we get to learn all the mistakes, the previous pioneering work, when they did this, what are some of the mistakes. So one of the number one, I wouldn't say mistake, but something that we could improve on, which is the way that how Droid was collected. So Droid was collected by like many institutions all around the world, right? So but the problem is that every trajectory has only one repeated trajectory. So if you're talking about picking up this pen, they only have one trajectory of picking up this exact pen. And that's good because you have so much diversity. But at the same time, diversity could actually hurt performance in some way, right? So for us, we focus on collecting 100 tasks, and every of these 100 tasks has on average 100 demonstrations. So in that sense, you could just basically train similar to like the large behavior model from TRI. You could also train diffusion policy on just this demonstration itself. You could actually get it working. So I think the idea is that not only just to have diversity in terms of tasks, but also having it able to repeat enough so that a policy could actually learn to sort of, on that meaningful skill that we want to capture. And I think Haoquan will talk about the training paradigm, but in general, we observe that training on MolmoAct dataset will give you about 5 to 10% performance increase, at least on the LIBERO benchmark, we are seeing that. And in the real world, we also see a slight performance increase.
Do you have any idea
Yeah,
what the trade-off is there? Like how much data do you need for each individual task to get good performance versus how much diversity do you want? Because like diversity is super important, of course, too.
Yeah, of course. Yeah. So I think Michael also asked the question in terms of like, did we do this in-house? We did it in-house. So in terms of how much I can scale this, it's really tough. And the problem is that we also want to have diversity. We have to have repeatability. And I think what we actually care the most about is quality. So what I mean by quality is that the data operators are, specifically trained with us way before they started collecting the data. And if you look at it, there's no need to actually filter through any of our data because there's no scenarios where the robot will just freeze there for like 3 seconds. So we ensure that there's mechanism in place that no ops does not occur. Everything is well captured. You're able to get, full observations of exactly what the robot is doing. And then for some of these tasks, we actually try to have like an iterative cycle where we run we take a few of these demonstrations, we run a simple diffusion policy to see whether, is the data good enough to at least overfit to that specific task. So that like this whole process of data collection in a very, I guess, a small scale, and allow us to have quality control over than just trying to collect millions of trajectory. So I think that's also something that, a lesson learned in that case.
You guys have any further question on kind of the MolmoAct dataset?
Now, I just want to say it's incredible. I can't imagine just the amount of actual operations work that.
How many hours of data is it? That's that. How many hours of data do you get?
So actually, it's not that much, like the amount of hours, if you convert it, it's about, I think, 22 to 25 hours. Yeah.
Okay. For 10,000,
it's
that makes sense.
not that much. Yeah.
What was the rejection rate? How much data did you throw out to get this data, to get this quality data set?
Well, that's a great question. So I think for at least for this one, there wasn't like any kind of rejection process because we ensure that there's a lot of mechanism in place that for the data to be able to even collect, is of a certain quality. Yeah. So there's no obviously the only times where you do rejection is like maybe that's about 500 to 1,000 where the camera is either there's only one camera that's working.
Okay.
Sometimes even if you're connected, sometimes the camera is not working.
So there are no cases like where you're like trying to pick up a cup and you drop it and you throw that out. That's still useful data.
Yeah, that's a great question. So when we collect these 100 demonstrations of 100 tasks, for that 100 we have well planned out to have a certain percentage of intention failure. So in a sense whereby we will intentionally fail and then have this kind of recovery actions to try to reattempt.
I see. Interesting. Do you think that has any ramifications downstream for like are intentional failures indistinguishable from unintentional failures? You never got unintentional failures?
No, we do have unintentional. It's more so we kind of record it. So like let's say we collect 100 demonstration, and then throughout this demonstration you kind of fail, and then you will just kind of know how much times you fail. So let's say like we want to keep the cap of these unintentional failures to around like 5 to 10 times if there's like 100 demonstration. So it's not like we intentionally try to fail, but just sort of we keep track of that. And then I think throughout this data collection period, we also like have quite like pretty manual supervision throughout all the data operators to kind of ensure this data quality as well. So that's why we weren't able to curate like the largest data set, but data quality is what we're really aiming for here.
Yeah, that was a similar point in the original Molmo, right? Where data quality was paramount. So similar. Okay. Nice. Okay, cool. Thanks.
All right. So I think I'll add on some stuff first. Yeah. So I'll talk briefly about how we enable our model to say predict the depth and the trajectory of the robot and the image observation. So what we did is that we add up a auxiliary or depth vocabulary of the size of 128. And these depth tokens are corresponding to a VQVAE codebook which also has like 128 discrete codebit embeddings. And then we first train a VQ-VAE on the same data set we have, but we have to train them on depth images. So we first generate all the depth images from a model called the depth anything V2. And then we use those depth images as the train data set to train a VQ-VAE with an encoder and a decoder and a codebook with both encoding and reconstructing loss. And then after that, we have a VQ-VAE encoder and the codebook that can encode those depth maps with high quality. We then use that model to just encode the depth maps we generated into different depth tokens. And we map those tokens into the vocabulary we have for the MolmoAct. So these depth tokens. And then for each image, we will have
corresponding set.
corresponding stats, like a string of different depth strings that contains of 128 depth tokens. And then for and then these depth tokens can also be reconstructed back using the decoder we train.
Can I? Yeah. So I can just mention here that, like you have these the reason why we use like, depth anything is kind of because these standard, a lot of these robot episode data, they don't give you the depth map immediately. So like our action reasoning data generation procedure can be applied to any like conventional robot data set. You can kind of generate these reasoning traces and augment it to these like action reasoning data. So even if your data only has like the input observation image, the language instruction, the action, you can always convert it. So for example, the process with depth is kind of just what Haoquan mentioned. And then what we did with these like visual reasoning trace generation is essentially we pass every image through Momo. So Momo will point to the trajectory, the gripper on every like frame in the episode, and then we will sequentially link them up. So we will basically like to basically take these points and then convert it into a line. So essentially we just choose like we kind of sample 5 points equally from this, the entire episode. So let's say like we're on time step 3, then we'll just take the point on time step 3 and then also take the point on the last time step and then samples 3 time step in the middle. And then that forms our visual reasoning trace, like 5 lines. So it will have like 4 segments each. Yeah.
I think these two components, the depth and the trace, they are also kind of what Jiafei said, is makes our model more interpretable. So for the trace, you can already saw in the video that we can see where the model wants to go. And the depth token are a little bit abstract, but you can always just decode that into a depth map using the VQ-VAE decoder we have. And for the reasoning process, it's just like whenever we take in the image and the language instructions, we first generate the depth, and then we generate the trace, and then we generate the action. So this is like an autoregressive process that allow us to do conditioning on previous reasoning steps. And then for the steerability, as we mentioned, what we do is that we first overlay the image, the visual trace onto the image with this image plus, and then we also provide the same language instruction, and then the model will directly gives the action. Because I think this choice is that we believe that whenever we provide the ground truth trace, the model can save some time instead of do the full reasoning. And then for the training process, so we basically have 3 different stages. So for the first one is that we follow the Momo's training pipeline to do like multimodal web data training, and also adding a lot of the data we curated using robot data and action reason data. And then in that stage, notably, we only have a single image in the training stages, but we don't want that because like we have a lot of downstream tasks that requires multiple image inputs. And we use single image. It's only because one thing is that a lot of the robot data doesn't have multi-view images, and the other one is that we follow the same convention that Momo used in their pre-training process. And that's why we have the second stage of training. It's called the mid-training, where we want to filter out a lot of the high-quality data where we collect it on our MolmoAct Dataset, and we also want to make our model to be more adapted into the scene that we want to test it on. So it has a lot of Franca tasks, and also a lot of the risk cameras, multi-camera views. So we wanted to get more high quality information, and that is more similar to what we want. And then in the pre-training stage, we use like 256 H100 and train for around 1 day, so 24 hours. And then for the mid-training, we use half of the GPUs, so 128 of H100, and then we train that for half a day, like 14 hours, something like that. And for the post-training, to make it more parameter efficient, we use LoRa fine-tuning, which can also like pretend the capability of the pre-trained models, and it's also converging faster. Basically, we usually use 32 to 64 H100 GPUs, and it takes around, say, 2-3 hours to maybe up to 10 hours, depending on different tasks. But it's a lot more efficient than doing full fine-tuning on this entire model. It's a 7B model, so it's a lot of parameters. Yeah. I think Jiafei can talk more about the evaluation results.
Yeah, so I think a lot of these things that, as what Haoquan just mentioned, is the standard kind of like training paradigm that vision language action models sort of adopt upon. I think, but I guess like it's also a bit specific, right, for our case, whereby we need to make sure MolmoAct work with the Momo vision backbone. So I think that's something that we actually test out and and also evaluate upon. So I think maybe to talk a bit about the evaluation, I think if Jason can go to the slide with simpler, the result is simpler. So I think one of the things that we actually first started with, which is to evaluate the quality of pre-training. So I think evaluating pre-training is really difficult. So if you look at, for example, Pi, and if you look at GR00T or any of these models, they have a huge amount of pre-training data that they collect themselves, and then they will evaluate on like their own environment, or even if they curate their own simulation that's within the data distribution of what they pre-train on, it will work really well. But if you just take that model after pre-train, try to deploy it on your own environment out of the box, it's going to be difficult to get it working, because essentially we are not at the scale of data of how language models or vision language model has been trained. So that level of generalization is just not seen yet in robotics. Unless you have so much pre-training data, then your pre-training sort of like covers the whole spectrum of every potential things that could happen for a specific robot. So the way we try to show this is that since we are training on this filter version of OXC, a good way to actually evaluate this is to evaluate on SimplerEnv, which is like a simulation benchmark that is a collaboration with UCSD and also Google. But what they did was that they have people to actually trace out or sort of like sketch out the same kind of visual distribution as compared to what they have collected using the RT1 dataset. And so now with this in the simulation, you're able to at least have a few tasks that falls within distribution of what you are pre-trained on. And then they also have another version, it's called variation aggregation, which is like similar tasks, but there's slight changes to camera position, the texture. It looks slightly out of distribution from what the pre-trained OXC dataset might contain. And then you help you to evaluate on generalization. So this is just to give the audience some context about like what we're actually evaluating for pre-training. And I think this is one of the more prominent environment that actually we could actually show pre-training able to be deployed zero shot. That means out of the box. And
So go ahead. I thought you were finishing up.
Yeah. So the thing is that since everyone is already training on OXC dataset or have some form of OXC dataset in their pre-training mix, so we are able to sort of compare with all these different models. And I think comparing with like many of these models from like GR00T to Pi to Magma, which is from Microsoft Research, and OpenVLA, they all have this OXC dataset mix inside. And I think the thing that sort of stood out to us is that actually Momo actually able to achieve one of the SOTA performance as compared to all these models for both visual matching and variation aggregation. Even though for just action data alone, Momo is only trained with 200K robot episodes, and for example, Pi is on like 1.2 million robot episodes. So the scale of data is totally different. And I think that is also one of the things that we try to show that, with reasoning, you're able to get more out of the same data. And I think that is what people in vision language, people in LLM or vision language models, they have also shown. For example, with chain of thought prompting, you're able to get better performance, although you're training on the same amount of data. And in the multi-model case, set of mark from Jianwei in Microsoft, you also show that, by prompting the model in a specific way, you're able to get better performance. So they're not actually adding new data. They're using the same data, but through this reasoning process, getting more out of it. Yeah. Sorry, Chris, I didn't have a question.
I was just going to say, this is a really fascinating table. And I feel like this is something that I've no one really compares these VLAs to each other, right? Like I feel like it's very hard to get a real head-to-head comparison of everything. So I was just looking through this, like so first of all, what's visual matching versus variant aggregation here? We have a bunch of questions.
Yeah. So visual matching, I think maybe is there a way that maybe Jason could pull out a picture? I think there might be a picture that shows.
I mean, we can go to Simpler's GitHub.
Sure. Yeah.
So let's say, this is the default OXE kind of fractal image that everyone trains on. So this is more like in what they call in visual matching. So they try to overlay this original image onto the simulator, so it gets as close as possible to the training image distribution. And then where variant aggregation is, they started adding in, let me see if I think I can find a paper, and they have a visualization. Yeah, so right here. So this is their visual matching, just trying to, add all these like green screen texture matching to get it as close to the in distribution, the training image as possible. And then in variant aggregation, they go back to this raw sim and then adding some variation. So I think they show some, I think it's possible to find some variation that they added. So these are like lighting, these are background changes. And then also, over here. So you can see like there are some lighting changes, making it a bit darker, making it a bit lighter, changing the background, changing the texture of the drawer, these things like that. That is part of the variant aggregation here.
Okay, so that would mean so the scores there are going to be like the average across like all the variations in lighting, background, texture, etc. So you do like a full grid of all these. Okay, so what's going on in some of these results then in that table? Like some of them are pretty like. For example, why is Groot missing in the variant aggregation column?
Yeah, so I think something about the result is that, as I say, many of these papers, they reported that they use OpenX embodiment in their training, correct? So, but there's also a bottleneck in a sense whereby they are also adding a ton of other data. So when you have a bunch of other data, inherently, I think you are sort of like bottleneck in that sense, because, you need to also consider that there might be a distribution shift between the different domains of data, especially for action data. So it's more sensitive. So in that case, I think like for certain models, they are actually inherently better for like deploying on humanoids, for example, Groot with a bunch of humanoid data, but they're not able to really do well in this specific domain. And I think the reason we didn't report variation aggregation is because we were actually looking for the right implementation of like Groot N1 in the sense whereby, we don't want to sort of implement in a way that is sort of misrepresenting what the model does. So we actually found a paper that have implemented Groot N1, and I think the best way we can trust is an academic published paper versus like some random GitHub repository that does an implementation. So we sort of cross-reference with that paper and show that, okay, it only works getting numbers for visual matching, but not so much of variation aggregation. But I think that right now people from NVIDIA or from like Gear team, they're actually working with us to sort of get, the pre-trained checkpoint on just on this simpler benchmark, so that we can actually also update the numbers. But in general, I think you can see that actually most of these models, as long as they are trained with OXE, they can sort of deploy zero shot or out of the box on the simulation and get some kind of performance.
You also talk about LIBERO.
Oh yeah, so that's for pre-training. So I think that's also one of the only ways we can really evaluate pre-training effectively, because we don't have this like huge amount of data that everyone else is using that they collect, and we are focused mostly on open sourcing everything, right? So that's for pre-training. So of course, after you have a really good pre-trained model, and I think there is a good relation to see that having a good base model will tend to yield a better model that can be used to easily fine-tune or efficient fine-tune for downstream tasks. So the way we also try to evaluate that aspect of it is that we use LIBERO. LIBERO is like one of the more common benchmark people use for post-training. Although I think the initial intention of LIBERO was not really meant for VLA post-training, but people have sort of adopted that for that specific purpose. And so they have a bunch. They have like some collected human tele-op demonstrations, and the idea is that you take your pre-trained model, you do fine-tune, either you do full fine-tune or LoRa fine-tune, and then you try to evaluate on a suite of like 4 categories, from spatial, object, goal, long, which is a long horizon task. And each task has about 10 different, each category has about 10 different tasks. So in total, we have about 40 different tasks. And then, of course, there's many ways we can try to compare with all the different models out there. But we actually specifically only compare with those models that does like fully auto-regressive, because as I think the audience, or maybe like you guys are also aware that, by providing more information, you actually get better performance, right? So for example, adding one more camera, adding proprioception state, this could all boost up the performance. But if let's say you want to just isolate the problem, then I think it's fair to only compare similar model architecture, which is fully auto-regressive. And if some other architecture uses like action experts, that actually also helps to boost a lot in the performance, because you're in a more continuous prediction rather than discrete. So I think these are things that we try to keep standardized. Of course, we are not claiming that this is the SOTA method in the whole of LIBERO, but this is like a really competitive method for at least all those methods that use auto-regressive, which means that they require some form of reasoning. So for example, I think one of the more prominent work is NVIDIA's ThinkAct that came out recently. So we also show that our model is able to outperform that reasoning model. And also maybe Jason can show the real world example.
So we also, okay, I'll show it.
Go ahead.
Yeah, no, I was we also do these like real world evaluation experiment on Franca, both with single arm and bimanual, to show that MolmoAct can also be adapted to another environment. Based on these different environments, we ran these trials across 25 trials per task. So we compare with also baseline like OpenVLA, which is like one of the most common open source VLAs from academia, and as well as Pi-0's fast version. So this is their autoregressive model using their, like, this is not using their, their full matching. And to specify like right here, because Pi-0 is, I don't think they're really tuned. I'm not sure if they really tuned out their LoRa configuration. So we follow their experimental procedure, which is to use full fine-tuning. But for OpenVLA and MolmoAct, we only use LoRa. So this is kind of to just to kind of follow their convention. And in terms of full fine-tuning, I think you get better performance compared to LoRa, because just you're tuning more parameters in this case. But then we collect around I think it's like 50 demonstration per each task, and then we fine-tune each of these models. It's like LoRa for VLA, OpenVLA, and then do full fine-tuning, and then LoRa for MolmoAct. And then we roll out per 25 task. And then you can see that MolmoAct, is well adapted to this downstream real world evaluation task. Even in bimanual as well, like Pi-0 has much more bimanual training data in their pre-training. But I think MolmoAct is still putting up like comparable numbers and outperforming Pi in this case. And then we also
sorry. I have a question, Jason. In MolmoAct's case, you guys use basically the visual tracing, right? So, but I believe it's more like to do with the N effector pose. So, but some of these tasks are maybe a bit more dexterous. Maybe you need to pick up the cloth, which is a deformable thing.
Yeah.
And I guess you have photo tower as well. How's your experience with those tasks that it seems to me it's not as straightforward as just having a visual trace, but it doesn't look like a struggle.
You mean like it's hard to represent these deformable tasks with visual trace?
Yeah, because it seems to me the visual trace is like, almost, I think of it almost like the path for the wrist. But then once you get really close to the object, then it's a lot more alert about the dexterous like handling and grasping. So I'm curious, because it seems to me the way you set it up, you guys haven't actually thought about it that way, but it seems to work. I was wondering whether is my intuition correct, or...
I think we in this case we are showing that with visual trace, because Pi and OpenVLA they don't have these visual trace. So I think we are showing that with visual trace it helps improve the performance. But I think as you say, like you get closer to these, because like these different, like for example Franca is 7 DOF. So with these like closer, more like let's say contact rich manipulation, it requires more dexterous manipulation. They are certainly better representation that I think in future works people can look into that are more effective compared to visual trace. It's like kind of extension. But I think in this case we're just showing that visual trace can help here. And then, but I think there's a certain, future works can definitely look into like different form of representation. It doesn't have to be a visual trace in this case.
Yeah, so I think to add on to Jason, and also to sort of better explain what to Michael why these things sort of work. I think if you think about it in a way that don't think of the visual trace as providing a really concrete precision kind of annotation. Think of it as providing you with a high level plan. And when humans write the plan, you still have a low-level policy that is sort of trained to actually predict the actual action. So similar to, VLA training, we are also learning in a supervised manner to learn the action. And all this comes back to behavior cloning, right? So I think one of the huge benefits of doing this is that now you're able to have that action-centric representation of learning how to fold a deformable object, but in the same time having a supervision to guide the action through like visual trace. So the visual trace comes as a high-level plan where, as a human, intuitively look at, we visualize this kind of plan ahead of time. And when we're executing, is relying on low-level motor skills. So I think sort of having this connection would be better to understand.
Okay, got it. Yeah, thanks for the explanation. I also want to ask, like, for the bimanual task, right? Is the model generating like, two different visual trays
I can show
at the
you
same
here.
time and making sure?
Yeah, so we have examples right here. But, and like in this bimanual, I can put the Franca experiment here. So, in the bimanual experiment, they will say the trajectory of the left end effector is this, the trajectory of the right end effector is this, and then it will predict, now it's 14 DOFs now. So it will predict 14 DOF action. And then since we're doing action chunking, there will be 8 chunks here. Whereas like, in like, I was just saying like in single arm, it will just be, the trajectory of the end effector is this. Yeah. And then predict the action in 7 DOF.
Yeah, I'm curious about this one since like I imagine the original data set is basically pretty much all single arm, right? So are you saying that basically the model somehow learns some kind of affordance where you don't have a case where, like one visual path, like, your right arm is kind of blocking the left arm to do something, especially when things are, I imagine folding tower can have that kind of situation, right? Do you think it's reasoning well enough to, like, let's say you add 4 Franca arms, like, would it be able to coordinate those effectively, you think?
No, we never tested with 4 Franca arms. So, so
I
know. But I think in this case, no, I mean, it's sort of like, are you asking like what, because we don't have these like, a lot of bimanual data in pre-training, you don't know if it's how well it translates to when we do it in post-training?
Yeah, it's like, I think having another arm like helps with more things, but you do have to be aware of what the other arm is doing and the order of which to do things. Like when you fold clothes, right arm do this first and then left arm do the other one, things like that. But if you do it the wrong way, there's 2 arms may collide into each other. So I was wondering if the reasoning, even though it's trained mainly from single arm, like does it translate to just when you just put 2 arms and then you figure that out? I suppose that also has some implication on cross embodiment down the road, right? When we start to have octopus, like 8 different arms doing all sort of things. Like, I'm just curious how you think about that.
Yeah, I think in our case, at least we show that, this reasoning still works. I mean, let's say OpenVLA, right? They didn't train with any bimanual setup in their pre-training phase, but, in downstream, they can still show that it's adaptable to bimanual setup. And kind of in the same way, we can do that too. And then we can show that, I feel like, these tasks, they are not like super long horizon. So maybe, I don't know if it's different task configuration, then you might run into different problems. But at least for these side of settings, you can show that the reasoning can still help assist well without running into too complicated tasks. And then, it's just two arms for now. So it's still able to draw out the lines on the image well, giving it some separation. And then I feel like Momo also do a good job being able to track like 2 different robot end effectors. So the actual like visual reasoning trace ground truth that we generate are also quite accurate enough. So when it's actually doing the deployment, MolmoAct can still predict these visual reasoning trace, the plans quite well enough so that both of them doesn't collide to each other.
Yeah, that's good.
I really like these reasoning traces. One thing about this, so you have these 2D trajectory lines. Why not? You have the depth map. I'm surprised that it's not predicting something in 3D, right? Like you could lift the depth. Or I guess maybe the LLM can't do that. Or why are you predicting in 2D?
So are you talking about implicitly predicting in 2D? So actually, like the way we saw through evaluation, where you show the observation, the model first of all output the depth perception token. I think the idea here is that these are not just random tokens, like people use like latent, representation, or they use some kind of like text token. The problem about this is that you're not able to ground it in any way. But when we present these, depth perception tokens, you're able to actually decode it and get back the 3D point cloud of the scene.
Right. Yeah.
So there is a form of grounding. And because it's fully auto-regressive, now you're continuously predicting the visual trace. So you're actually using the information from this depth scene to sort of implicitly predict what is that visual trace. So I would say that it's not that we didn't use, but it's more of like now the visual trace is depth enhanced in some context.
Yeah,
then-
right. Yeah, I understand. Like it has the 3D information implicitly, right? But like when I'm trying to translate that to robot motion, like if going like 2 inches from my face is pretty different from going half a meter from my face, right? In this 2D
for sure.
image that you can see here. So like it's surprising to me that it doesn't have that, I guess, so that it doesn't need that to solve
It
problems.
doesn't need. Yeah, so I
Like
think
the reasoning trace part, like to do the reasoning, I would expect it to help to be able to avoid objects better or something, to get less failures.
yeah, of course. So I think we did see that behavior. So I think maybe Haoquan just now mentioned about the steerability. So when you're still steering it, we are basically just conditioning on the visual trace alone without any additional depth token. And we realize that actually that is not as efficient as, of course, we have also ablation experiment where you remove depth token completely just with the line. You realize that both of them are outputting the exact same line, but one of them will have a better sense of depth in the sense whereby if you run it 10 times, the grass might succeed more often with the one that is conditioned the depth. So there's also like evidence that we see that, because if you draw 2 lines on the image, it could be exact same, but there's no sense of how deep it is. Yeah.
So I guess is the idea that with the depth conditioning, it's like the final decoding will handle this, and that the depth decoding is something kind of implicitly handling it, but that's okay. And that so this 2D information the 2D trajectory representation doesn't end up really losing anything because it can still make these inferences.
That's the idea. Yeah.
Okay, cool. Can you provide a depth image as input to skip the reasoning steps? Since you just mentioned skipping the depth prediction,
that's
can I just like toss one in so make it easier? Yeah.
Yeah, so that's a good question. That's actually something we are continuously exploring.
Okay.
I mean, because like when we are doing this right now, we back then we didn't really have that part. Obviously you could actually essentially just input in depth, right?
Right.
You have a RGBD camera, you can get the actual ground truth depth rather than using depth anything. But I mean, there might be some tricks to need to be done in terms of making sure that there's enough augmentation to the pre-training process of using this kind of depth image. When you use depth anything, it's a relative depth. Whereas like when you use something like from depth sensor, you're getting more precision.
Yeah, because depth anything P2 is still only giving you relative, right? Not metric depth. Okay, fair enough.
Yeah. So for here, I think 2 things that we're trying to show. One is that MolmoAct is more generalizable. So it comes back to the first video that we're trying to show that when we are filming this thing, the environment that we collect data and when the film crew came is kind of different because there's a bunch of lightings. So we show that also MolmoAct is more generalizable in terms of going beyond its training distribution. And at the same time, the mid-training, we also show that it actually helps. When we evaluate in the real world, you see about, as I mentioned, 5% performance boost in terms of using mid-training versus not having mid-training at all. So I think the mid-training actually helps to better align the model towards, downstream fine-tuning. Or at least for this case, when we test this on Franca, we see there's a positive transfer. And Jason, if you can scroll down a bit more. So I think this is also another very interesting thing that we actually did ourselves. So I think one idea is to look at, how much can this kind of line steerability be evaluated. So I mean, previous work or even like the recent work that came out from like Gemini, Gemini embodied reasoning model, they actually care a lot about these pointing features, right? So moving one level above that is that how good is line steerability? That means in terms of if you give the model just an instruction, how good it is to actually generate these coordinates in such a way that you can sketch out a meaningful trajectory line. And that is useful because like this gives you some kind of understandable, interpretable plans of what the robot is able to just condition on this language. And we actually compare with both Gemini and GPT, and also with Hamster. Hamster is a hierarchical VLA model from Dieter's group, and this one actually also they specifically train a VLM that's able to output lines and then have a low-level policy that's conditioned on this line as the input. And the way you sort of evaluate this is that this is kind of subjective, like person A might find line 1 is better than person B, and person C might find line 2 is better. So to make sure that, we have a fair evaluation, we actually use the ELO rating, the same kind of rating that people use in chatbot arena, I think Carl uses in robot arena also. So I think from there, we actually see that with a huge sample size of, I think we collected about 1,500 votes, and we curated a bunch of images from the internet, and then we actually get people to propose some of the prompts, and we have about over 1,500 votes to sort of do a A/B comparison, and we see that people has a huge preference over the output that MolmoAct gives. So this also helps us to actually have a better understanding that MolmoAct could actually give much more interpretable output that humans could actually understand. So if you look at this example here, like which one do you think that most represent the instruction of pick up the toy, fish, and place into a basket? So I think so that's the one of the ablation experiment that we actually did to try to better understand how this idea of line steerability could be useful. So it's useful in the sense you have to first of all understand the intent of this model through this line prediction. And if Jason could go down further. So this is also another very interesting experiment that we ran. So I think in this case, we want to see that how much or how far you can sort of stretch your language variation in terms of like prompting some of this model without any fine tuning. So we actually designed about, I think, 6 different scenarios. These are tasks that, didn't exist in SimplerEnv. It was never part of the OXE dataset. And then these 6 scenarios, maybe if Jason, you can scroll down to the bottom, you can show them what these 6 scenarios looks like in the appendix. And all the objects that you see in these 6 scenarios, I won't say all, but most of the objects you see in these scenarios, they doesn't exist in the original OXE dataset. So these are new objects that we actually have like 3D designer that sort of like creator, and then we throw into the environment itself. Yeah, it's a really long technical report. So if you look at these are very interesting scenarios. Right? We have scenarios of cubes, just random cubes on the table. We have scenario with like fork and objects, and we have scenario with like Obama and Taylor Swift. That's like the iconic kind of setup people use to compare. We have like bowls, pens, and more precise in sort of like putting the pen into the cuff tart. And if Jason, if you can go back to the previous one, the result. So what we did was that we actually compared to OpenVLA and spatial VLA in the sense whereby these are 2 models that's heavily trained on OXE. So we know that it will actually work better zero shot compared to like other models that has a mix of other data. And the way we sort of test this is that we provide users, I think about 10 participants, these 6 scenes, and we ask them to come up with interesting prompts. And these are purely open-ended prompts. So it could be like put the red ball into the cup, into the bowl. It could be flip the red ball. It could be take the red ball and cover the red bull. So any kind of arbitrary language instruction that is feasible in this environment, and then we run all these instructions on these models and generate trajectory rollout. So the idea here is that not to actually evaluate whether the model is able to succeed, but rather whether it's able to even do something meaningful. So I think this comes down to the point whereby we want to show that in this pre-training evaluation, can we see some kind of like early stage generalization or contextualization of this kind of model to be at least in the same domain doing things that's meaningful. There's always this notion in robotics whereby we might not even know when the ChatGPT MolmoAct robotics comes. This could be like one of the example where you see something doing something meaningful. And then, of course, it doesn't make sense because there's no success condition. It's all open-ended. So we also have users to actually do like a ERO rating. We have over 1,000 votes. And people compare to see whether which model is actually doing something that's more sensible towards their open-ended instruction. So this is it's an interesting experiment, and we want to sort of see how good some of this pre-training actually helps, and whether also to give us an assessment whether it's reasoning the way forward to sort of reach that moment. I think that's what Chris mentioned in his tweet, at that GPT moment of robotics.
You want to talk about your
Yeah.
Yeah, sure.
Yeah, I think maybe Haoquan can talk about this.
Yeah, so we also evaluated how steerable our model is in terms of overlaying the line onto the image, like how well the model can follow that trace. So, so when we are usually trying to evaluate the model, like these VLA policies in real world, so we basically just try to collect some demonstrations and then fine tune the model on that. We call that post-training stage. And then we deploy the model to that task. During the evaluation process, usually people would just give the ground truth language instruction to the model. So exactly the same as what they train the model on. And then they let the model just operate the task and execute in real world. In terms of steerability, we want the user to come in and interact with the model. And sometimes, in our case, there are 2 ways to let the user to prompt and to interact with the model. One is to use the visual trace. So the user can draw the visual trace to let the model change the direction or change the plane of its task. And the other one is just let the user to prompt something in language, and then just trying to change the objective of the model. And notice that whenever the user tries to draw the line on the image, it won't be the ground truth line. There always be some offset because like the other one is predicted by Momo by pointing, and then align with the temporal aggregation. And then the user will just draw it based on preference. So the line will always be out of distribution. So to make a fair comparison, we also changed the language instruction. We changed the verb, changed the adjective or even the noun to make it a little bit varied from the ground truth. So we have a table on this. Yeah. This one. So the ground truth task is just to say, pick up the pick up the orange bowl. And then you can see that we sometimes change it to lift up the dirty bowl or just pick up the bowl on the left. So all of these are open language instructions. And we found that actually when we use the trace to direct the robot to different bowls, the success rate is a lot higher than using these open vocabularies. And we can scroll back. Yeah, and then we also compare this open instruction using the same instructions that we curated in the table with other models like Pi-0 Fast. And we found that actually, even in terms of open instruction following, MolmoAct is still better than Pi. I think this is because we leverage more of the VLM's capability of reasoning in language tokens. Yeah, but overall, using visual trace, I think giving a visual hint to the model is still more steerable to let the user to prompt the model in terms of success rate.
Sorry, how do I interpret this chart? So when you say task progression, presumably the higher the better. But what exactly does, for example, 0.42 means?
So this is so we repeat the task, the evaluation for 10 trials, and for each trial we record the success progression of this task. So we have the rubrics for how we calculate these task progressions. So for example, if we, I think in appendix we have that. I think if we move to the, I think we should go to the appendix to see the detail. Say the last one. Yeah, here is it. So if after the prompt, either visual trace or the change of language instruction, the model can go to the correct direction of the new bowl. We give it at 0.5. If it grasps onto the bowl, and then we consider it as the 0.85, and then if it lift up the bowl, it's the full score for that. And then we compute the average of 10 trials to get the final number. So with visual trace, it's around 0.75, and with open instruction, it's like 0.4, I think, so 40%. Yeah, 0.42. And for Pi, like I think the language following is not that strong, so it's like 0.13. Yes.
I see. Got it. Okay, cool. So basically, since MolmoAct have two like really trained properly on visual trace and also like just a broader open instruction, you can be more flowery, let's say, with your language instructions, or like and also implement with visual, and then just get you closer to actually the task completion, right? Yeah. Okay, got it. Yeah. Obviously, I mean, I imagine most laymen, eventually when these things actually is in production, probably have no time to visual trace, but they probably want to talk. And I think the open instruction will be really critical at that point. Yeah.
Yeah, I just give people lots of options. I feel like people are good at solving problems.
Also to sort of add on to this point, which is that if you think about it, like language has that natural, behavior of ambiguity, which is that, how can you really describe something that is like purely grounded on image, right? So there's a huge study of like vision language grounding. And I guess in this context, even going one step further, grounding not just on the vision space, but also into action itself. So I think having that connection, because, for example, like you can describe these two cups in many different ways, but the policy might not be able to, sort of relate their instructions to what the distribution of the data was trained on, or the specific, target that is supposed to go. But now by giving this visual trace, you realize that, okay, maybe when times where language is hard to describe, it's easier for you to just, sketch on the iPad or interface. And as what Chris was mentioning, you're giving people more options rather than just solely rely on language alone.
No, I think this sort of work I also been exploring previous works like RT trajectory from Google, and then even like Hamster. So like a language variation for the same task might be there might be a lot of different language instructions that you can be described to describe this task, but each of these language instruction for the same task, they might have the same trace. So the robot might learn a trace much easier than it has to learn like all these different language instructions. So it's kind of like from previous work, like RT trajectory will show like having a trajectory input might be better than just language input in this case. Yeah,
I think that's all for the results evaluation part. Yeah, we have a lot of details on like the data set examples and training framework. And a lot of details in the appendix. This is, as Jiafei says, a very, very long technical report.
No, I mean,
it is,
Feel free to explore
which is great.
if you're like,
Very
I know you
true,
guys
yeah.
were kind of interested about data mixture, so I can give a more kind of explanation here. So like, for example, this is like fractal, bridge, and then these are like BCZ. So this is what we use in pre-training. You see, it's just a single image from view image, and then it predicts like these depth, and then the line, and then the action. Then we also predict, given like these same images, we also predict line only. So you can see it only predicts the trajectory in this case. And then on the other hand, given this image, we only predict the depth token. So these are the auxiliary depth token prediction task. And then on the over here, we also have these trajectory condition action data. So, you know, we overlay a line onto the observation image. And again, these are all the same data set, but we just create so many different modes of data. Given this, we ask this, you know, based on the image of the annotated trajectory, what is the action that the robot should take? So now it learns these trajectory condition data, which can be used to steer. And then, you know, some of these multi-web data example from Pixmal and the captioning. And then this is where like examples of MolmoAct datasets. So you see like MolmoAct dataset has two views essentially, from like the front view and the wrist view. But then each of these tasks, they also have two side views. But then, so that, you know, here we can predict, I mean, we show the home environments for MolmoAct dataset, but we also show these tabletop scenes. So these will be like knock down, you know, unload the plates, unload the mug. So these are more like atomic, what we call like atomic task. But right here is more like these household relevant tasks, like lift the pillow or clean the toilet, etc. And then finally, these are like the examples that we have from our experiments in the post-training case. So, you know, we have put the ball in the sink, that this is what we evaluate on. So again, we also train on like just a front image and a wrist view image. Like, you know, you kind of see how MolmoAct dataset can help, because it's quite similar to what MolmoAct dataset is in the mid-training phase. So this is why we think, you know, having like this mid-training stage with MolmoAct dataset kind of increase our performance in our downstream case, where especially like with the Franca scene in the household environment, doing these type of tasks is very relevant to MolmoAct dataset. Is kind of also what we design MolmoAct dataset for, you know, the specific cases to align MolmoAct better with these household environments tasks that we want to do ultimately. And then these are like the bimanual scene we showed earlier with like the front view, and then the left wrist view and the right wrist view. And then, you know, we also show different example with like rainbow. This is kind of what we have in our demo videos.
I think an add-on to MolmoAct dataset is that just to note that our real-world evaluation, they share the same configuration, like same robot, the Franca robot, and same cameras, like a front camera and a wrist camera. But we're not, like the MolmoAct dataset is collected in a totally different place. So we're not leaking our evaluation into the MolmoAct dataset. So not trying to get a huge advantage by doing that. And we also do some ablation showing that even without MolmoAct dataset, I think mentioned by Jiafei, it's still better than a lot of the current baselines.
I think also one thing to sort of point out, I mean, like, of course, like this is the first attempt at this kind of model. We're also learning along the way. So if you look at the output, you realize there's so many tokens there. And compared to like, you know, OpenVLA, which predicts like 7 tokens and represented by the least used 256 tokens, you know, the idea here is that because you're predicting so many tokens in an auto-regressive manner, you're naturally going to get a disadvantage in terms of speed. But then, you know, moving forward, as we are going to, you know, embark on hopefully MolmoAct V2, we realize that actually maybe reasoning is not something that you do at every time step. Because humans don't reason at every time step. We only reason when we want to reason. And I think having that notion in mind, I'm not going to say more, but, you know, having that notion in mind sort of give us the inspiration towards how we can actually make this thing better and make it more faster.
Yeah, that makes a lot of sense. One other thing, though, is that like all the reasoning model, like your Gemini or DeepSeek or O1, O3, whatever, they all like continue to reason. Have you thought about doing something like world modeling, like have it predict the result of the world after the trajectory and then go back and reason again until it is ready or something? Not sure how you even get that data.
Yeah, so I think there's a lot of like you know, bets on like different approach, right? People with like thinking that maybe world model could be the solution, simulation. You know, I think these are all, you know, excellent approach, and I think there's a lot of potential in many ways we can actually lead towards solving. I would say solving robotics, but hitting that sort of like GPT moment. And I guess like one of the reasons we didn't really look into using world model is because after all there is still going to be a grounding process, and you either learn an inverse dynamics model or you have some kind of ways to sort of ground that generation from world model and output like actionable visual motor signals. So I think there might be ways that sort of can, better paper that came out might be able to sort of narrow that gap. But I guess for our case, I think we did not explore into that yet, because we feel that, at least in computer vision, there is a lot of ways you can actually ground reasoning. This kind of approach, even as simple as bounding box, reasoning over bounding box could be also an approach that can solve ground reasoning. And I guess like we try to sort of explore that space first before, looking into like other potential alternative, or at least when we see like a necessary sort of like a bottleneck that's sort of like stopping us, from getting better models out of this kind of reasoning process, then maybe that could be an approach that we also look into.
And I think it's also like, all of these different companies or different institutions trying different approaches for these robotics foundation model. Some they use human video, some they learn from simulation data, or from only pure robot action data in real world. But then, I feel like reasoning can be applied to all of this case, so it's not actually like mutually exclusive with anyone's approaches. We're kind of just saying like, if you add in reasoning to whatever your approach is, we think that this is like a viable way to help improve your performance and lead to like better and more generalizable models.
Yeah, I mean, I guess my original point was more that like reasoning obviously is great, but reasoning in like the more traditional context is planning. Right? It's like I'm imagining some perspective futures and trying to figure out whether or not all the facts mesh. And here you're predicting auxiliary losses, but this is like step one towards full reasoning, right? There's lots of other stuff that could happen. I could imagine at least, right? But no.
Yeah. I think that there could be a lot of other ways of sort of we can explore this. And I think the whole notion of why we're trying to propose a reasoning action model as a new class of this kind of robotics foundation model is that we are still trying to also figure out what's the best way of doing reasoning for robotics. And we're just showing like this is a starting point. There could be other ways of representing reasoning. I guess also in language model context, there's many ways reasoning could come out from. Either from test time inference or through like pre-training stage. So I think there's many alternatives, and I do agree. I think these are things that hopefully pushing this idea of that maybe reasoning could be a way forward. There's more work that's going to come out that leverage on different ways of doing reasoning that's meaningful for robotics.
I think like
go ahead. I think also one of the most important reasons that why we sort of turn into reasoning is because I think Imia, which he gave the talk on test of time last year, Nuris did mention that pre-training sort of hits is going to sort of like his end because of like data is like a fossil fuel, right? So I guess in robotics, data is not even a fossil fuel yet because we haven't even mined all the data that's out there. So maybe and I think you also have an article that mentioned that if we try to collect robot data in the scale of language model, it's going to take about I guess like 40,000 years or something along the lines. That's not that scalable. So I guess maybe we should also look into other alternative of how do we get more out of less data.
Yeah, it's very cool. Really thought-provoking paper. Very cool stuff. Thanks.
Yeah, I mean, I think really, really great job, guys. And also the fact that you guys, I know it's not just the doing the work, but also actually preparing everything to be open source. Yeah, you guys should like go to the the Hugging Face page just to share it again. So all this, I'm sure, is not trivial to clean up. Have it ready. Yeah, so I think great job, guys. Putting it out there. Yeah, maybe just to wrap things up. I guess. Next steps, and maybe Jiafei, you alluded a little bit to it. Like maybe some of the angles you guys are thinking about is being a little bit more thoughtful about when to do reasoning, so that you can have a bit of speed up of the whole thing in production. Any other things that you guys are thinking about that could be useful for future work?
No, I was also saying like I think we're not saying like this the depth perception tokens and the visual reasoning trace is the ultimate form of reasoning. I feel like there's so many other possibilities out there, and then we're also kind of excited to see what, if we can inspire future works to come up with like better ways of reasoning than this. Yeah,
there should be a lot of intermediates for reasoning, like what Chris mentioned, like maybe 3D trajectory, the other kind of reasoning, maybe do some more planning, as what you mentioned. I think there's a lot of possibilities to do reasoning, and we just trying to lift up this one of its kind of VLA called action reasoning models. And this is just our first version of how we explore on this type of model. There should be a lot of other options which are open for debate.
Yeah, and also to sort of give a bit of a teaser of like what might come next. I think the idea is that we are still going to follow along, AI tools mission and vision of, providing this kind of open source models that is, inspectable by the community, and also hopefully, can benefit people that wants to build, this kind of robotics foundation model from scratch. Because if you think about it, everything that MolmoAct sort of represent is fully end-to-end open source, goes all the way down to the language model itself. And I think that's really cool, right? Because in that sense, you are able to inspect and really understand what goes down the hood much better. And I think to also think about what is the next step, as what Jason and Haoquan mentioned, we want to look into, other forms of, how can we sort of represent reasoning, and how can we sort of couple reasoning with action learning. Because at the end of the day, there is going to be a spectrum where you have models that can do really good textual skills, with like language, the large behavior model from TRI. And you're going to have like really good embodied reasoning models like Gemini. But maybe the way to do it is to find an intersection where you're able to do good skills and also at the same time leverage the power of reasoning to solve some of the tasks that you couldn't solve. So finding that balance seems like why we have in mind, moving forward to the next step.
Yeah, just to your earlier point, Jiafei, about like, it's obviously a great service you guys are doing to the community. I do want to point out though, non-trivial compute has been burned in the process of this.
Yeah. So we are also pretty open about that in terms of how much compute we are burning. But yeah, I think in a relative scheme of things, I think the compute that we are using is pretty small. Yeah.
I don't know if
Depends
I
on
believe
relative
that.
to who.
Okay.
You took to all the...
Yeah, relative to like the largest scope. Yeah. If that makes sense.
Yeah.
Yeah, not everyone has $75 million from the NSF. Is that what you guys got a couple weeks ago?
Yeah. Well, yeah, it's part of
But
I mean, still great that you guys are being so transparent. I mean, even on the compute side, I mean, to be honest, it's not like me and Chris trying to rub it in. It's but you guys are very transparent about the level of compute you're using. This is what it takes to do the work you guys do. I think it's good.
Yeah, I think also like comes back to the point, which is that we really encourage everyone to sort of read this 61-page report, because it goes all the way down to exactly what task progress actually mean. Like, exactly how we assign task progress. I think down to really small details like what actually the vocabulary even looks like that we used for the action tokenization. So I think these are all very interesting things. Hopefully the community is able to sort of learn, and also we're also able to learn from work that's all built on top of MolmoAct.
Yeah. I also really like the ELOs thing, the ELO ranking. Even though it sounds subjective, but it is probably the only way to really compare between models, in the real world setting. I know RoboArena did it, and it's good to see you guys doing it as well. Hopefully more will do the same.
Yeah, I think thanks to your contribution also for evaluating RoboArena. I think we are sort of pushing.
yeah. If you go to RoboArena, I think for robots do like most of it. But anyway, I don't want to shoot my own project, but yeah. But it's good to see ELO. Like it's so hard to do like the traditional control, like the classical, like ablation study. It's just maybe more straightforward to just do like blind tests, like it's like Pepsi versus Coke, and then let people say what's their preference. It's like you say, a lot of it is very open ended, especially when the models are not good enough to completely finish a task, and maybe there are very very different ways to finish a task anyway, especially for the more long horizon tasks. So maybe the ELO way kind of ranking like policies is a good.
Yeah, definitely. I think that helps us to have a glance forward in, I think everyone will agree that evaluation is a bottleneck, and everyone is trying to figure out what's the best way to do evaluation, and at least having some glance forward in time. What is the potential outlook of having this kind of robotics foundation model, and what people can sort of agree upon. I think that's definitely, and also to sort of throw in a bit more teaser towards what MolmoAct V2 might be like. We hope that it can be something that can deploy out of the box, in a sense whereby we get rid of the fine-tuning process, at least for very specific domains. So that's like something like, I guess like also because like that allows us to actually, see wide adoption or deployment, rather than, because not everyone has that, compute and resource to do that fine-tuning. So
this is maybe one of our longest episodes, but it's all very well spent, I thought. Thank you so much for making the time. Yeah, maybe the last question that we always ask, is do you guys have any papers that you want to give a shout out to that you come across recently? Doesn't have to do with reasoning in robotics, but you also want to give a shout out to. Maybe we can get those authors to come on the pod as well.
Wait, is this how it was done previously? I remember you asked me this question in the first broadcast.
Yeah. Basically, with this is how we close the pod. Yeah, every episode. Yeah.
Oh, really? Yeah. Okay, interesting. But do you guys get the author that I say in the first episode?
Oh, I can't remember which one you asked.
Yeah, who did you say? Do you remember?
I don't think we actually follow up properly. But actually, we did have a lot. Subsequently, we did have a lot of follow up podcasts because of someone's recommendation in the previous pods. Yeah, obviously, me and Chris do it in our free time, and so there are just so many good papers. But yeah, anyway, what are some of your cool papers you read recently?
So maybe I'll just throw out one. I think one of the work that sort of like really stands out recently, as long as we are doing this action reasoning model, is this work from NVIDIA which is called ThinkAct, which is a vision language action reasoning model that uses like reinforced visual latent planning. I think this is very interesting. They did a dual system approach where they try to bridge the high level reasoning with the low level execution and sort of reinforce it with visual latent planning. And I think this is something that has really good performance. In fact, I think and yeah, it's for a different team in NVIDIA, but it's pretty interesting. I think I will recommend this paper.
Yeah. Cool. National Taiwan University. Jason, Haoquan, any cool papers you wanna give a shout out to?
Oh, I actually was thinking about this because it's quite related in the sense that but they're just doing it in language. But this is actually something we're also looking at. Came out right before our release.
Yeah, this is a very good paper, actually. It's very interesting.
Okay, all right. We absolutely need to talk to these guys then.
Yeah, 3 votes for this paper.
Get on the
All
pod.
right, great.
Yeah, okay, cool. Okay. All right, okay. Yeah, well, anyway, thanks again for making the time, guys. It's really great work. Thanks for open sourcing so much, putting it out there. I'm sure there'll be a lot of other work that will build on top of what you guys have.
Looking forward to MolmoAct 2 as well.
Yeah,
that's awesome. Okay, cool. Thank you so much. We'll see you, I guess, in the next one.
Okay.